Hello, my dear sleepless friends, and welcome to Hafi Sleep, a place where we quiet the mind and expand the imagination, where we trade the day's worries for the wonders of the cosmos. As you settle in, letting your body grow heavy and your breathing slow, I want to invite you on a journey, not just any journey, but the greatest voyage of the mind you can possibly take. We're not just crossing a border or an ocean tonight. We're leaving our entire world, our solar system, even our galaxy behind. We are going on a pilgrimage, 2.5 million light years into the depths of space, to visit our nearest giant galactic neighbor, a swirling island of stars so vast it defies comprehension, a place of ancient light and profound mystery, the Andromeda Galaxy. Now close your eyes if you wish. Picture yourself floating, weightless, in the serene blackness of space. The Earth is a distant blue-green jewel far behind you. You turn your head, and there it is. Not a sharp, brilliant point, like a star, but a soft, ethereal, elongated smudge of light. It looks like a little cloud, a wisp of cosmic cotton candy caught in the black velvet of the night. To the unaided eye, from our backyards on Earth, that's all it is, a faint, mysterious blur. But we know, don't we? We know that this gentle smudge is, in reality, a colossal pinwheel of 1 trillion suns, a swirling vortex of star stuff so enormous that if you could hold it in your hand, our entire Milky Way would feel like a little sibling. For centuries, that's all it was known as, the little cloud. The astronomers of old, from Persia to France, saw it and cataloged it as a nebula, a cloud of gas within our own galaxy. They had no idea of the truth, no conception of the scale of what they were truly looking at. The discovery of what the Andromeda Galaxy truly is a story of human curiosity, of technological advancement, and of a single, brilliant mind who dared to look at that faint smudge and question everything. Our story begins not with a powerful telescope, but with the naked human eye. Imagine a time before electric lights, when the night sky was a brilliant, overwhelming tapestry. In 964 AD, a Persian astronomer named Abd al-Rahman al-Sufi was compiling his book of fixed stars. He was a keen observer, meticulously mapping the heavens. And he saw it. That little patch of light in the constellation of Andromeda. He described it as a little cloud. He was the first person in recorded history to note this celestial object, though it was almost certainly seen by countless unknown skywatchers for millennia before him. For centuries after al-Sufi, the Andromeda Nebula, as it became known, was just a curiosity. When telescopes were invented in the 17th century, astronomers like Simon Marius in 1612 got a clearer look. He described its glow as the light of a candle seen through horn, a beautifully poetic way to describe its diffuse, soft light. But still, no one knew what it was. The prevailing idea was that our Milky Way galaxy was the entire universe. All stars, all nebulae, everything existed within this one grand starry system. So this little cloud in Andromeda, it had to be a cloud of glowing gas, a nebula, relatively close by. Perhaps a solar system in the process of formation. It was a logical assumption, but it was wrong. The mystery deepened throughout the 18th and 19th centuries. Telescopes got better and better. With each improvement, astronomers could see more detail in the Andromeda Nebula. It wasn't just a formless blob. It began to reveal a structure. It had a bright, star-like center, and spiral arms could be faintly glimpsed. The great Lord Rosse, using his massive 72-inch telescope in Ireland in the 1840s, was the first to sketch the spiral structure of certain nebulae. He saw these whirling pinwheel shapes and was utterly baffled by them. What were they? How could a cloud of gas take on such a complex, structured form? The technology of the time couldn't provide an answer. The key to unlocking the mystery lay not in seeing the structure of the nebula, but in seeing individual points of light within it. The turn of the 20th century was a golden age for astronomy. Photography was revolutionizing the field. Instead of relying on an astronomer's eye at the eyepiece for a fleeting moment, glass photographic plates could collect light for hours, revealing faint details invisible to the human eye. And at the forefront of this revolution was the new 100-inch Hooker telescope at Mount Wilson Observatory in California, the largest telescope in the world at the time. It was here that our story reaches its climax, with a man named Edwin Hubble. Hubble was a unique character, a brilliant astronomer who also possessed the flair of a debonair aristocrat. He used the immense power of the Hooker telescope to peer into the heart of the Andromeda Nebula. His target was a particular kind of star, a Cepheid variable. Now let's pause for a moment to understand why these stars are so important. A Cepheid variable is a special type of star that pulsates rhythmically, growing brighter and dimmer over a regular period. In 1908, the brilliant astronomer Henrietta Swan Leavitt had discovered a crucial relationship. The longer the period of this brightness pulsation, the more intrinsically luminous the star actually is. Think of it like this. If you see two light bulbs from a distance, and one is flickering slowly and the other quickly, and you know that the slow flickering bulb is always a 100-watt bulb and the fast one is a 40-watt bulb, you can figure out how far away they are by how bright they appear to you. The Cepheid variable stars were the universe's standard candles. They allowed astronomers to measure cosmic distances. So, in 1923, Edwin Hubble pointed the 100-inch telescope at Andromeda, and, using the new photographic plates, he did the impossible. He found not one, but several Cepheid variables within the Andromeda Nebula. He measured their pulsation periods, which told him their true, incredible luminosity. Then he looked at how faint they appeared in his photographs. The discrepancy was staggering. The only way these stars could be so intrinsically bright, yet appear so faint to us, was if they were mind-bogglingly far away. His calculations placed them at a distance of nearly 1 million light-years. This was a number that shook astronomy to its core. At the time, the estimated size of our entire Milky Way galaxy was only about 100,000 light-years across. Hubble had proven that the Andromeda Nebula was not a cloud within our galaxy. It was far, far outside it. It was an island universe in its own right, a galaxy, just like our own, but even larger. The announcement was a scientific earthquake. Overnight, the universe expanded exponentially. Our Milky Way was no longer the entirety of creation. It was just one galaxy among, as we now know, potentially 2 trillion others. That faint little smudge in the sky was, in fact, the Andromeda Galaxy. This discovery was the birth of modern extragalactic astronomy, and it all hinged on those tiny, pulsating points of light Hubble found in that photograph. He had looked at the little cloud and saw a universe of stars. It was one of the most profound and humbling realizations in human history. So now, with the identity of our target confirmed, let's truly get to know this behemoth, our galactic neighbor. Let's start with the basics. Where is it? How do you find it? If you're lucky enough to have a dark sky away from city lights, you can actually see the Andromeda Galaxy with your own eyes. It's the most distant object visible without a telescope. On a clear, moonless night, look for the constellation of Cassiopeia, that familiar W or M shape in the sky. Now, from there, you can star hop to the constellation Andromeda, which is home to a string of moderately bright stars. The galaxy appears as a faint, elongated smudge of light near the star New Andromeda. It's subtle. You won't see spiral arms or a brilliant core. You'll see that same little cloud that Al-Sufi saw over 1,000 years ago. But now, when you see it, you can know the truth. You are looking at the combined light of 1 trillion stars, a light that left on its journey to your eyeball when early humans were just learning to use stone tools. You are looking back in time, across an ocean of space so vast it numbs the mind. And just how vast is it? The distance is almost incomprehensible. We said Hubble initially measured it at about 1 million light years. Our measurements have gotten more precise since then. The current best estimate places the Andromeda Galaxy at 2.5 million light years from Earth. Let's try to wrap our heads around that number. A light year is the distance light travels in 1 year. Light moves at a constant universal speed of 186,282 miles per second. That's so fast it could circle the Earth more than 7 times in a single second. Now imagine that unimaginable speed and keep it up for an entire year. The distance it covers in that year is 1 light year. It's about 5.88 trillion miles. Now, multiply that by 2.5 million. That's the distance to Andromeda. It is a gulf of emptiness so profound that it takes the fastest thing in the universe 2.5 million years to cross it. The light you see from Andromeda tonight began its journey when the ancestors of humanity were roaming the plains of Africa. Every photon that hits your retina is a prehistoric messenger. Now let's talk about the scale of the galaxy itself. Our Milky Way is a large barred spiral galaxy, about 100,000 light years in diameter. It's home to an estimated 100 to 400 billion stars. For a long time we thought the Andromeda Galaxy was smaller, but we now know it's the big sister. Andromeda is a monster. It spans a whopping 220,000 light years in diameter. That means from one end to the other, it would take light 220,000 years to travel across it. And the number of stars? Hold on to your hat. While the Milky Way has a few 100 billion stars, Andromeda is thought to contain a full trillion stars. 1 trillion. That's a 1 with 12 zeros after it. 1,000, 1,000, 1,000, 1,000. It's difficult to even conceptualize such a number. If you tried to count to 1 trillion, counting one number per second, without stopping, it would take you over 31,000 years. Every one of those trillion is a sun. Many likely have their own families of planets, their own moons, their own asteroids and comets. The sheer amount of real estate in that one galaxy is beyond human imagination. What does this colossal entity look like up close? If we could travel outside of our own galaxy and look back at it, the Milky Way would probably look quite similar to what we see when we look at Andromeda, a beautiful grand design spiral galaxy. Andromeda is classified as an SA's-B galaxy. Let's break that down. The S means it's a spiral. The A means it has a prominent central bulge without a large bar structure cutting through it, though recent evidence suggests it might have a small, weak bar, so it's sometimes called SBB. The S indicates that its spiral arms emerge directly from the bulge rather than from the ends of a bar or from a ring, and the B describes how tightly wound the spiral arms are. B is intermediate, not too tight and not too loose. So, picture a brilliant, yellowish-orange central bulge, a vast, dense swarm of mostly older stars. This bulge is like the galaxy's downtown, where stars are packed tightly together. If you were on a planet in the bulge, your night sky would never be truly dark. it would be perpetually lit by the glow of countless nearby stars. Emanating from this central bulge are two majestic spiral arms, which are labeled, rather unpoetically, as the P1 and P2 arms. These arms are not solid structures. Think of them like traffic jams on a cosmic freeway. They are density waves, regions where the gravitational pull causes gas and dust to compress. This compression triggers the birth of new stars, so the spiral arms are essentially stellar nurseries, lined with bright blue young massive stars and the vast glowing clouds of hydrogen gas, the HII regions, from which they are born. These arms are studded with brilliant blue star clusters and pinkish nebulae, creating a stark and beautiful contrast against the darker lanes of cosmic dust that weave through them. This dust, primarily carbon and silicate grains, is the soot from long-dead stars, and it obscures the light from the stars behind it, creating the intricate dark patterns we see in photographs. Surrounding the entire disk of the galaxy is a vast, diffuse halo of stars. This halo is spherical in shape and contains some of the oldest stars in the galaxy, as well as mysterious dark matter, which we'll get to soon. The halo isn't uniform. It's also home to over 450 globular clusters. Globular clusters are magnificent, ancient spheres of hundreds of thousands of stars, all gravitationally bound together in a tight ball. They are some of the oldest structures in the universe, and Andromeda has a rich collection of them, far more than the Milky Way's 150 or so. Studying these clusters helps us understand the very early history of galaxy formation. Now let's journey to the very heart of Andromeda, to its galactic center. This is a place of extreme density and power. At the very core, like most large galaxies, Andromeda is believed to host a supermassive black hole. In the Milky Way, our central black hole, Sagittarius A, has a mass of about 4 million times that of our Sun. Andromeda's central black hole is a true monster. Estimates place its mass at a staggering 100 million solar masses, 100 million suns, crushed into a single point of infinite density. Thankfully, it's currently quiet, a sleeping giant. It's not actively devouring large amounts of matter, so it's not shining as an active galactic nucleus or a quasar, but its presence is felt through its immense gravitational pull, dictating the orbits of the stars, whizzing around it at incredible speeds. The stars in the immediate vicinity of this black hole are orbiting at velocities that are hard to fathom, providing astronomers with the evidence needed to calculate the black hole's mass. This region is a cosmic maelstrom, a place where the laws of physics as we know them are pushed to their limits. The gravitational tides there would rip any star or planet apart. It's a violent, chaotic engine room at the center of an otherwise majestic and serene-looking structure. Let's talk about the life cycle of stars within Andromeda. Just like in our own galaxy, it's a continuous cycle of birth, life, and death. The spiral arms are the primary sites of stellar birth. Giant molecular clouds, vast complexes of cold gas and dust, collapse under their own gravity. Within these dark, cold wombs, knots of material form and begin to heat up. When the pressure and temperature at the core of one of these knots become high enough to fuse hydrogen into helium, a star is born. We see this happening all over Andromeda. The most famous star-forming region in Andromeda is actually a whole satellite galaxy, but we'll get to that. Within its main body, there are brilliant blue regions filled with O and B type stars, hot, massive, and short-lived stars that flood their surroundings with intense ultraviolet radiation, causing the surrounding hydrogen gas to glow with a characteristic pinkish red color. These are the HII regions. supernova can, for a brief period, outshine an entire galaxy of stars. Andromeda, with its trillion stars, has supernovae going off relatively frequently. In fact, the first supernova ever recorded in another galaxy was in Andromeda, back in 1885. It was called S Andromedae, and at its peak, it was visible in small telescopes, a testament to the sheer power of these stellar explosions. These explosions seed the galaxy with heavy elements, the oxygen we breathe, the carbon in our bodies, the iron in our blood, all forged in the hearts of stars and scattered across the galaxy by their violent deaths. This enriched material then becomes part of the next generation of stars and planets, continuing the cycle of cosmic recycling. But not all stars go out with a bang. Smaller stars, like our Sun, live for billions of years and end their lives more quietly, puffing off their outer layers to form beautiful planetary nebulae and leaving behind a white dwarf core. And the very lowest mass stars will shine for trillions of years, far longer than the current age of the universe. Andromeda has a full spectrum of these stellar populations, from the brilliant blue newborn giants to the faint red ancient dwarfs. One of the most fascinating aspects of Andromeda is its retinue of satellite galaxies. Just as the Milky Way has the large and small Magellanic Clouds and several dwarf spheroidal galaxies orbiting it, Andromeda has its own entourage. The most famous and obvious of these is Messier 32, or M32. M32 is a compact elliptical galaxy that appears as a bright star-like blob right next to the central bulge of Andromeda in small telescopes. It's an enigmatic object. It's incredibly dense for its size, and astronomers believe it may be the remnant core of a much larger galaxy that was mostly stripped away and devoured by Andromeda in a past galactic encounter. It's a galactic ghost, a survivor of a cosmic collision. The other prominent satellite is Messier 110, or M110. This is a more standard dwarf elliptical galaxy, a fuzzy oval-shaped patch of light. It's less dense than M32 and seems to be a more pristine example of a small galaxy. But the most spectacular satellite by far is the Triangulum Galaxy, also known as Messier 33. While M32 and M110 are dwarfs, M33 is a full-fledged spiral galaxy in its own right, the third largest member of our local group of galaxies after Andromeda and the Milky Way. It's about 50,000 light-years across and is a beautiful face-on spiral. The relationship between Andromeda and Triangulum is complex. They may be gravitationally bound to each other, with Triangulum possibly orbiting the mighty Andromeda. In total, Andromeda is known to have over 30 small dwarf galaxies orbiting it, like moons around a giant planet. Studying these satellites is crucial because they help us map the distribution of dark matter around Andromeda. The way they move is dictated by the gravity of the unseen dark matter halo that envelops the entire Andromeda system. Dark matter. We can't talk about galaxies without mentioning this, the universe's greatest mystery. What we see of Andromeda, all the stars, the gas, the dust, is only a small fraction of its total mass. The vast majority of the mass in Andromeda is invisible. We cannot see it. We cannot touch it. We don't even know what it's made of. We only know it's there because of its gravitational effects. The stars in the outer regions of Andromeda's disk are orbiting the center far too quickly for the amount of visible matter there is. The only explanation is that the galaxy is embedded in a huge, massive halo of something that doesn't emit or absorb light. Dark matter. This halo is thought to be roughly spherical and extend far, far beyond the visible edge of the galaxy. It's the dark matter's gravity, that holds the entire galaxy together, preventing it from flying apart as it spins. Without this unseen anchor, Andromeda would have torn itself apart long ago. So, when you look at an image of Andromeda, remember, you are only seeing the luminous tip of a vast, dark iceberg. Now, let's talk about the most dramatic chapter in Andromeda's story, one that is still to come. Its future collision with our own Milky Way galaxy. Because Andromeda is our closest giant galactic neighbor, and because the universe is expanding in a way that allows nearby objects to be gravitationally bound, we are not drifting apart. We are, in fact, on a collision course. The Andromeda Galaxy is hurtling towards us at a speed of about 110 kilometers per second. That's 250,000 miles per hour. Don't panic, though. The distance is so vast that this cosmic car crash is still billions of years in the future. Current predictions say the two galaxies will begin to merge in about 4.5 billion years. What will this be like? It will be the most spectacular light show in the history of our solar system, but it's unlikely to be a violent event for individual stars. Galaxies are mostly empty space. The actual chance of two stars colliding is astronomically small, so our sun and solar system will probably survive the encounter physically unscathed. But the night sky will be transformed. As Andromeda approaches, it will grow larger and larger in the sky, eventually stretching from horizon to horizon. Then, as the two galaxies begin their gravitational dance, they will swing past each other, their shapes distorted by immense tidal forces. Long streams of stars and gas will be pulled out, creating brilliant bridges and tails of light across the heavens. The two central black holes will eventually find each other and merge, sending powerful ripples, called gravitational waves, through the fabric of space-time. After this first close pass, the galaxies will swing back around and merge completely, their stars and gas mixing together over the course of another 1 billion or 2 years. The result will be a new giant galaxy. Astronomers call this future object Milkdromeda, or Milkomeda. It will likely be an elliptical galaxy, a large, fuzzy, football-shaped collection of stars, without the distinctive spiral arms of its progenitors. The process of merging will trigger a massive burst of new star formation as clouds of gas collide and compress. The sky from a planet in Milkdromeda would be filled with the blended light of 1.5 trillion stars, a testament to a colossal union that began when the universe was only about 2/3 its current age. This future merger puts our own place in the cosmos into perspective. Galaxies are not static, unchanging islands. They are dynamic, evolving entities that grow, change, and interact over cosmic time. Our Milky Way has a history of cannibalizing smaller galaxies, and Andromeda does too. The impending collision is just the next logical step in this cosmic dance. How do we know all of this? How have we been able to unravel the secrets of this distant smudge of light? It's through decades of painstaking observation using every tool at our disposal. After Hubble's groundbreaking work, astronomers continued to study Andromeda with ever more powerful telescopes. The Palomar Observatory, the Kitt Peak National Observatory, and many others contributed detailed photographs and spectroscopic data. Spectroscopy allowed astronomers to analyze the light from Andromeda, determining its composition, the motion of its stars, and its rotation. A major leap forward came with the Hubble Space Telescope. Freed from the blurring effects of Earth's atmosphere, Hubble has provided stunningly detailed images of Andromeda, resolving individual stars not just in the outskirts, but all the way into its crowded bulge. One of its most ambitious projects was the panchromatic Hubble Andromeda Treasury (PAT) survey, which imaged a large portion of Andromeda's disk in multiple wavelengths. This survey allowed astronomers to study the demographics of its stars in unprecedented detail, creating a galactic family album. But to see the big picture, you need a wide-field view. That's where ground-based telescopes with huge fields of view come in, like the Subaru telescope in Hawaii. They have captured magnificent full-color images of the entire galaxy, revealing the delicate structures of its dust lanes and the faint, extended halo of stars. And then there are space telescopes that see in other wavelengths. The Spitzer Space Telescope observed Andromeda in the infrared, peering through the dust to see the older stellar population and the heat from dust itself. The Chandra X-ray Observatory has seen the high-energy universe of Andromeda, the hot gas in its halo, the remnants of supernova explosions, and binary star systems where material is being sucked onto a neutron star or black hole, glowing with X-rays. The Galactic satellite mapped Andromeda in ultraviolet light, highlighting the regions of hot, young stars. Each wavelength of light tells a different part of the story. By combining all these views, the optical, the infrared, the ultraviolet, the X-ray, we can build a comprehensive, multi-layered understanding of this complex system. It's like investigating a city by looking at its visual appearance, its heat signature, its radio transmissions, and its nighttime lights. Each perspective reveals a different facet of its life and structure. Let's delve a little deeper into some of the specific fascinating features within Andromeda. Remember we mentioned the most famous star-forming region? That's not actually in Andromeda, but in its satellite, the Triangulum Galaxy M33. It's called NGC 604. It's one of the largest known HII regions in the local universe. If it were at the same distance as the Orion Nebula, the famous star-forming region in our own galaxy, it would be so bright it would cast shadows on Earth. It's a colossal cavern of glowing gas over 1,500 light-years across, lit up by a central cluster of massive, hot stars. Within Andromeda itself, there are countless brilliant star clusters and nebulae. Astronomers have cataloged thousands of them. There are open clusters, loose groupings of young blue stars that form together from the same cloud. And there are the ancient globular clusters we mentioned, orbiting in the halo. One of the most interesting things about Andromeda's globular clusters is that they appear to be of two distinct populations. One group is very similar to the clusters in the Milky Way, but another group is redder and seems to have a different chemical composition. This is likely evidence of Andromeda's violent past, having cannibalized smaller galaxies and absorbed their cluster systems. The galaxy's history is written in the properties of these ancient star clusters. Another fascinating area of study is the galactic disk's rotation. Like the Milky Way, Andromeda rotates, but not like a solid wheel. It exhibits differential rotation, meaning the inner parts rotate faster than the outer parts. By carefully measuring the Doppler shifts in the light from stars and gas clouds across the disk, astronomers have mapped out this rotation curve. It was the flatness of this rotation curve at large distances that provided some of the first strong evidence for dark matter. The stars on the outskirts were moving just as fast as those near the center, implying the presence of a huge amount of unseen mass holding them in their orbits. Let's talk about the interstellar medium of Andromeda, the stuff between the stars. It's not empty. It's filled with gas, mostly hydrogen, in various forms. There's cold neutral hydrogen gas, known as HI, which can be mapped using radio telescopes. These maps show a vast, extended disk of gas that often stretches even beyond the visible stellar disk. Then there's the warm, ionized hydrogen, HII, that makes up the glowing nebulae. And there's also molecular hydrogen, H2, which is much harder to detect directly, but is traced by the carbon monoxide, CO, gas that exists alongside it in the cold, dense molecular clouds where stars are born. Studying the distribution and motion of all this gas helps us understand the dynamics of the galaxy and the fuel for future star formation. One of the most ambitious observational projects in recent years has been the sealing of the individual motions of thousands of stars within Andromeda. Using the Hubble Space Telescope over a period of several years, astronomers were able to track the tiny, proper motions of stars in Andromeda's halo. This is an incredibly difficult measurement because the motions are so small from such a great distance. It's like watching a snail move on the surface of the moon from Earth. But this data was crucial for understanding the future collision with the Milky Way. It allowed scientists to measure the sideways motion of Andromeda, confirming that a direct collision is indeed inevitable. The study of Andromeda is also a window into the past and future of our own galaxy. Because we are inside the Milky Way, it's very difficult to get a global perspective. We can't easily see its overall shape and structure. Andromeda, being a similar type of galaxy, serves as a perfect analog. By studying its spiral structure, its bulge, its halo, and its satellite system, we can infer much about our own galactic home. It's like having a blueprint of your own house from the outside. Furthermore, because Andromeda is the closest large galaxy, it is a laboratory for testing our theories of galaxy formation and evolution. The prevailing model, the lambda cold dark matter model, suggests that large galaxies like Andromeda and the Milky Way grew hierarchically. They started as small overdensities in the early universe and grew by merging with and accreting smaller protogalaxies over billions of years. The evidence for this is written in the stellar halo of Andromeda. Detailed surveys have discovered faint streams and shells of stars in its halo, which are the ghostly remnants of smaller galaxies that were torn apart and consumed by Andromeda's gravity. It's a galactic archaeological site, with the fossil records of past mergers visible in the distribution of its oldest stars. As we bring our journey to a close, let's reflect on the sheer scale of what we've explored. From a faint, enigmatic smudge in the night sky, the Andromeda Galaxy has been revealed as a titan, a swirling metropolis of 1 trillion stars, a dynamic system with a violent past and an even more dramatic future. It is a key to understanding our place in the cosmos, a reminder that our galaxy is not alone, but part of a small, local family that is destined to merge into one. The story of Andromeda is the story of modern astronomy itself. It's a tale of how human curiosity, coupled with technological ingenuity, can peel back the layers of a cosmic onion, revealing truths more wonderful and humbling than we could ever have imagined. That little cloud is a universe unto itself, filled with star clusters and nebulae, with planets, and almost certainly with the potential for life. Somewhere among those trillion stars on a world orbiting one of them, another being might be looking out into the cosmic dark, towards a faint, milky smudge of light they call their own little cloud, unaware that they are gazing back at us, at the Milky Way. Let's talk about the interstellar medium of Andromeda, the stuff between the stars. It's not empty. It's filled with gas, mostly hydrogen, in various forms. There's cold, neutral hydrogen gas, known as HI, which can be mapped using radio telescopes. These maps show a vast extended disk of gas that often stretches even beyond the visible stellar disk. Then there's the warm, ionized hydrogen, HII, that makes up the glowing nebulae. And there's also molecular hydrogen, H2, which is much harder to detect directly, but is traced by the carbon monoxide, CO gas, that exists alongside it in the cold, dense molecular clouds where stars are born. Studying the distribution and motion of all this gas helps us understand the dynamics of the galaxy and the fuel for future star formation. One of the most ambitious observational projects in recent years has been the Liang of the individual motions of thousands of stars within Andromeda. Using the Hubble Space Telescope over a period of several years, astronomers were able to track the tiny, proper motions of stars in Andromeda's halo. This is an incredibly difficult measurement because the motions are so small from such a great distance. It's like watching a snail move on the surface of the moon from Earth. But this data was crucial for understanding the future collision with the Milky Way. It allowed scientists to measure the sideways motion of Andromeda, confirming that a direct collision is indeed inevitable. The study of Andromeda is also a window into the past and future of our own galaxy. Because we are inside the Milky Way, it's very difficult to get a global perspective. We can't easily see its overall shape and structure. Andromeda, being a similar type of galaxy, serves as a perfect analog. By studying its spiral structure, its bulge, its halo, and its satellite system, we can infer much about our own galactic home. It's like having a blueprint of your own house from the outside. Furthermore, because Andromeda is the closest large galaxy, it is a laboratory for testing our theories of galaxy formation and evolution. The prevailing model, the lambda cold dark matter model, suggests that large galaxies like Andromeda and the Milky Way grew hierarchically. They started as small overdensities in the early universe and grew by merging with and accreting smaller protogalaxies over billions of years. The evidence for this is written in the stellar halo of Andromeda. Detailed surveys have discovered faint streams and shells of stars in its halo, which are the ghostly remnants of smaller galaxies that were torn apart and consumed by Andromeda's gravity. It's a galactic archaeological site, with the fossil records of past mergers visible in the distribution of its oldest stars. As we bring our journey to a close, let's reflect on the sheer scale of what we've explored. From a faint, enigmatic smudge in the night sky, the Andromeda Galaxy has been revealed as a titan, a swirling metropolis of 1 trillion stars, a dynamic system with a violent past and an even more dramatic future. It is a key to understanding our place in the cosmos, a reminder that our galaxy is not alone, but part of a small, local family that is destined to merge into one. The story of Andromeda is the story of modern astronomy itself. It's a tale of how human curiosity, coupled with technological ingenuity, can peel back the layers of a cosmic onion, revealing truths more wonderful and humbling than we could ever have imagined. That little cloud is a universe unto itself, filled with star clusters and nebulae, with planets, and almost certainly with the potential for life. Somewhere among those trillion stars, on a world orbiting one of them, another being might be looking out into the cosmic dark, towards a faint, milky smudge of light they call their own little cloud, unaware that they are gazing back at us, at the Milky Way. And so, as you drift towards sleep, let your mind float in that vast interstellar space. Picture the gentle, stately rotation of that great pinwheel, its spiral arms turning once every few 100 million years. See the brilliant blue clusters of newborn stars, the faint red glow of ancient giants, the dark weaving lanes of cosmic dust. Feel the immense, silent presence of the dark matter halo, the unseen hand that holds it all together. And know that you are connected to it all. The atoms in your body, the iron in your blood, the calcium in your bones were forged in the hearts of stars long dead, in galaxies far away, perhaps even in Andromeda itself. We are not just observers of the cosmos, we are a part of it. We are star stuff, contemplating the stars. So, rest now, dear friend. Let the grandeur of the Andromeda Galaxy fill your dreams with wonder and your mind with peace. The universe is vast, beautiful, and you have a place within it. Sleep well.